All right, so before the break, we went over a concept of deep networks, how it has evolved from regular neural networks to mainly convolutional neural networks. And the fundamental difference that you saw over here once again was that rather than creating multiple layers, the first layers are basically learning features but not trying to classify, not trying to break it into a decision boundary, right? So in a deep CNN, as we discussed, we'll create many of these CNN layers. But in the end, we'll put a regular neural network. And then we will do the classification. So this way, we're not violating the universal approximation theorem. It's still a single hidden layer with some outputs over here. And here, we are essentially, think of it as if we are doing some kind of pre-processing. But rather than us having it learn something explicit from the data, I will learn the features itself. Okay. Now, some of you who have taken computer vision class before would remember we covered a technique called principal component analysis. Even if you don't know it, don't worry about it. But one of the jobs of the PCA is to take some input data. Okay, then transform it to some typically lower dimensional data, such that the data for different classes can be separated out a little bit better, and then we feed it to a regular neural network, which does the classification. So prior to deep convolutional networks, this was a pretty standard approach. Given some data, apply a PCA or some equivalent of a PCA, which gives you some features, then based on the features, try to classify the data, right? But we have discovered that if we feed the data ourselves, meaning feed the data and have it learn what's important, the feature itself. Features itself, it does a much better job of classification. Okay? So later on, I'll show you some examples of face recognition and so on, using this type of concept, and you'll see what a beautiful job it does. Okay? Anyway, just a couple of small comments on the overview of the course before I start going in depth into each technique. Okay, so one of the topics that I'm excited about, like I was mentioning, is called variational autoencoders. Let me present a high-level idea. Remember earlier I was saying, to be good in this field, you need to have a good visualization capability of the math. You should be decent in programming. And also you should be a good thinker. Thinker in terms of meaning, what are the possibilities out there? So good imagination is very important to being good in this field. So let me see if you guys can see that. I'll give you an example. So the way the variational autoencoder works is, so first let me explain the idea of an autoencoder. The way the autoencoder works is you feed in some inputs. It's a neural network, or it can be a neural network. Okay, so let's take the same example of our 784 input data, which is basically digits, 28 by 28, like a 0 or a 9 type of thing. Okay, so we feed the inputs to a network. So there will be 784 inputs, right? Let's pretend we use 100 neurons in the hidden layer. Okay, so this is our hidden layer. Okay, Then we put 784 neurons in the output layer. Sorry, 784. Okay, so again, all dense connections. Okay. So in an autoencoder, what we try to do is, remember, anytime we train a neural network, we give it some input, and there's an expected output. Okay. So in an autoencoder, the expected output is the same as input, as an example. Okay. So in other words, if I gave it a digit 0, I'm having it output also these 784. See that this dimension matches exactly the input dimension. So I'm having it also produce the same data. Okay. However, as you can see, what is it doing? Taking 784 inputs and compressing it down to how many in this example? 100. Then what is this part doing? Or decompressing it, right? So essentially, as you can see, we're having it learn compression, then decompression, okay? So after it has learned, one possibility would be we removed, so the weights have been learned, and now we fix these weights. So whatever it learned, we gave it many examples, 0 to 0, 1 to 1, 2 to 2, many kinds of 2s, many kinds of 3s. So suppose we did the back propagation, it learned the weights over here, learned the weights over here, but this one we don't care. We eliminate this after it has learned. Okay, then we feed these 100 inputs to a regular neural network classifier. And again, we have 10 outputs, 0 through 9. So sorry, total 10 outputs, right? So compare this approach to a regular approach. We just have a neural network as a classifier. We feed in 784 inputs and 10 outputs, a single hidden neuron there. Which one do you think will perform better? Okay, and why? Okay, see, anytime you come across these things, always start to question, okay, so that you can develop more insight into it. The reason this autoencoder approach will work better is because if you take a look at, for example, the digit 0, what's important over here? Is this data important over here? No. Only important part is this part, right? So once we compress it to only 100 things out of 784, you can think of it, perhaps what we are doing is we are making it learn what is important. So later on, I'll go into the theory of it and show you that indeed, this autoencoder performs a nonlinear PCA, but it's learning by itself through the data, so therefore it works better, right? Okay.
But if the regular neural network also has a hidden layer of 100 neurons, how is that different from the previous thing?
How is a deep network?
That if it also has a hidden layer that with 100 neurons.
100 neurons, right?
How is it different from the first model of the?
From the first model, because in this model, if you take a look, any input we give it goes through the compression stage, gets compressed to 100 before feeding forward, right? Over here, all 784 are basically feeding to a hidden layer. Okay, 100 then. So this is basically doing the classification. There is really no, I mean, it's not the compression we made it learn. Because remember, this part was learned so that we compress and decompress. So it's not, whereas in this case, these weights were learned to help it classify between the 10 digits. So if you think about it a little bit more, you'll be able to see it. That this is basically helping, these weights are helping it it distinguished. Whereas these weights are helping it compress so that it could be decompressed to the same point. So there's a difference between the two. Okay, anyway, so now let me come to a question for you guys. Okay, suppose we compress, we decompress, so let me put that decompression back. Okay, so we train it on many, many examples. It has learned these weights, it has learned these weights, right? Okay, now suppose I feed in the number 2. Feed in the number 2. Okay, so we'll compress it. It will give me the compressed representation for 2, right? Whatever those outputs are. Okay, now suppose I separate the last part out. And there's no first part over here. So basically there are 100 inputs and 784 outputs. Okay, what if I feed in the same compressed representation for the number 2 that I had learned from here? What will it produce on the output? What digit will it produce?
2.
If it was the compressed representation of 2, what I fed in here, it will be 2. Everybody agrees? Same way, what if I fed in 3, what will be the output? The compressed representation of 3 that I learned from here. 3. What if I feed in 2 and slightly change one of the numbers over here? Then what will it produce?
It will be 2, but slightly different from
2, but slightly different, exactly. So essentially, now we can start to generate artificial data. Okay. How is this similar to? Let me give you an example of us as humans. Okay. Do we have a compressed code?
yes.
What decides the color of our eyes or the color of our skin or how tall we are? DNA. So what is DNA in analogy to this?
Numbers.
It's the compressed code. So if we modify the DNA, we can change somebody how, if they had a disease or whatever, we can remove that, right? So this is the exciting field of variational autoencoders, where nobody has so far tried to break it down in terms of genes, like a human representation has. Okay, so it's just an idea that I'm trying with one of the PhD students. Let's break it into individual units, each unit over here responsible for encoding, like a genetic or a gene information, so that based on that, the output it produces is can be controlled in a certain way. Okay, so if it's a person, we want to make the person's eye color to come out green. We can modify this compressed representation and recreate it. Anyway, so
is this how they are producing new human faces with AI?
yes, with the variational autoencoders, but they haven't gone into the DNA breakdown like I'm thinking. Okay. Anyway, the great news about the deep learning field is it's so fast changing. I won't be surprised by the time we are done, somebody already has come up with a scheme like this, right? So keep your imagination open. If you have some ideas, my job is to teach you all the techniques so that you guys can apply those great imaginative ideas and take the AI to the next level. Okay?
Question. In order for this to work, will not you have to train each number by itself so that you have the DNA from each number? Because usually you will just train all of them.
Yeah, so once I go into the theory of the variational autoencoders, as we come up with the compression schemes, you will see we create individual distributions over here. It's not straightforward like I showed you over here. So wait till that part comes in over here. Anyway, Now let's start with learning some in-depth, the math behind it, the programming. So at least today, let me show you one example of training a network. Okay, so when we train a network, so suppose here's a neural network. Okay, in the beginning, like I said, I'll just focus on regular neural networks. After a couple of weeks, I'll switch to convolutional networks, then recursive networks, and so on. So basically, as we discussed, we have an input, we have an expected output. Okay, we have an actual output. Okay, the model is the term that we use, which represents the weights and the biases. Okay, so weights and biases. Of neurons involved. Okay, so our goal is create some kind of a loss function or error function. Okay, and based on the loss function, do the backpropagation and adjust these weights. Okay, so as you will see, it is essentially a mathematical optimization problem that we are trying to solve as we backpropagate, because we are trying to optimize the loss, meaning make the loss as low as possible, right? Okay, so let me, for today, give you a very, very small example so that you can understand the math behind it a little bit easier. Okay, suppose you're given some data, and the data looks like this. Okay, and all I do is ask you, fit this data, pretend this is a two-dimensional data, fit it with a line so that the line, even though not every point is on the line, but the line, if we compare the error with respect to each point, the overall loss is as small as possible. Okay, so what's the equation of the line? Mx plus c, or let me just say ax plus b, you know, think of b as, so one coefficient a, one coefficient b, it doesn't matter, okay? So from an optimization point of view, how will I define the error? I will define the error to be a of xi plus b minus y of I will be the error, right? And if I square it, because sometimes, you know, it will be negative, sometimes it will be positive, the magnitude can easily be handled by a squared error, right? So if I am given n data points, this will be my cost function or loss function or error function, okay? So again, this is very similar to what I described in the beginning when I was picking y equal to 2x plus 3, right? Okay, the question is, what are we trying to determine? What's our goal over here? Goal obviously is to minimize E, okay, such that, I should say, or let me rephrase it. Goal is to determine model parameters that result in minimizing our loss function or the error function. Okay. Okay. So what are the model parameters in our example?
Weights and
In this equation? No, this has nothing to do with neural network now. Okay.
A and B.
A and B are the model parameters, right? So your goal is to determine A that will minimize E. Determine A and B that will minimize E for each one of these given data points. So N is the number of data points that's given to us, right? So anytime minimization is involved, if you remember from your basic calculus, you take the derivative and set it equal to 0, right? So how will we do it? We'll do partial E over partial A, set it to 0. That will give us one equation. Partial E over partial B, set it equal to 0. That will give us the second equation. Solve the two equations for all the data points and you have the answer, okay? So let's take a look at the partial E over partial A, okay? If you've forgotten that, remember the partial E over partial E. Oh, sorry, partial E over partial A. First, we take this 2 over here, okay? So then this will be 2 I equal to 1 to n a of xi plus b minus y of I squared. So this, sorry, squared 2 came over here, right? Then we further have to multiply this by the partial derivative with respect to a of the inside term. If I take the partial derivative of yi with respect to a, it will be a constant. Derivative of a constant is 0, right? Similarly, b with respect to a, 0. Axi with respect to a, xi. So this will be my answer. Okay. Now, very similarly, let's go to partial E over partial B. 2I equal to 1 to n. A of xi plus b minus yi. And now, with respect to b, right? So this with respect to b will be 0. What about this with respect to b? 1. Okay? And this with respect to b will be 0, right? So I get two equations. Okay, now all I have to do is start plugging in the numbers over here. And by the way, both equal to 0. Both equal to 0. So suppose some data point is given to us, x equal to 3, y equal to 5, for example, right? So you will go to this equation, you'll put 3, 5, right? And this will be 3 in this example, and set it to equal to 0. Same way, you'll go to the second data point, third data point, fourth data point, keep adding all of these. In the end, what we'll come up with will be something like 37a plus 87b equal to 123. So if you were given 10, 20 data points, if you added them all up, all of these will become some coefficients, and some coefficient to the b. So this will be our equation 1. Very similarly, I don't know, 89a plus 231b, 841. So we'll get two equations, right? How do we solve this for a and b?
Substitution.
We can do a simple substitution, or we can convert it to a matrix form. In the matrix form, as you can see, this will be 37, 87, 89, 231, a, b equal to 123, 841, right? So what's the value of a and b? Will be the inverse of this if I multiply both by the inverse, right? So 123, 841 multiplied by, in this example, 37, 87, 89, 231 inverse. So this is my answer. Okay, provided whatever data points were given, result in these equations, right? Everybody agrees? Okay, so in this particular case, okay, remember this has nothing to do with the neural networks. All I'm showing you is if you are given a cost function, you are given some parameters that you wanted to optimize such that this cost function produces as low of a value as possible. Okay, then you simply set up the cost function. You take the partial derivatives with respect to the model parameters and set them equal to 0, and then solve the equations, plug in the data for all the data points, solve the two equations, and you will know the model parameters. So in this example, there is no need for an iteration. Okay, remember in the beginning I showed you we had an epoch, we looped over it, then we looped over many epochs, right? So there it's slightly different, but here, and by the way, the technique I showed you where we come up with the cost function, do the partial derivatives, the mathematical technique is called least squares optimization. Linear least squares. Okay, so let me show you a Python code for the whole thing, where we'll plot the graph. I'll run it through this data, and you'll see. And whatever I'm showing you, I'll put it on the website so that you can try it on your own. So, but anyway, before I erase it, makes sense, right? Pretty easy? Okay. Okay, so I'll show you a small PowerPoint with the code as well. Just a little bit better. Okay, so anyway, it's 4 or 5 slides very quickly. So like I said, the technique was called linear least squares optimization, and I'll show you the similar simple graph fitting example. Okay, main idea as we discussed, approximating the parameters of a model to a given data. Okay, and it has a lot of applications which we'll talk about later. But anyway, the technique is like I said, it's called linear least squares optimization. Okay, so linear refers to the parameters, not the data. Meaning, it doesn't mean that we are always fitting the data by a straight line. We could have a nonlinear curve as well, in which case our parameters will be beta 0, beta 1, beta 2. Okay. So based on the data, it will determine what the beta will be. So this linear part basically means there's no square involved with the model parameters. These are simply to the first power. Okay. Okay. So. Just like we discussed on the board, the cost function, like I said, sometimes we use the term cost, sometimes we use the word error, sometimes we use the word loss function. They all mean the same thing. So for this is the value for 1 point minus whatever was the expected, as an example. Then if we square it, minimize it for all points. So this is just like we discussed on the board. We take the two partial derivatives. They will be multiplied by 1, but I didn't write it, so that's the two equations as we discussed. Now let me quickly show you an example. So suppose this is the data given to us, 1, x of 1, y of 5.2, x of 2, 6.7, and so on. So if we plug that into our model, remember our model was axi plus b minus y of I squared, right? Partial e over partial a. And there was multiplied by x of I equal to 0, right?
2 times a over ax of I.
Oh, there was 2, yes, that was, sorry. Two, yeah, once we did the partial, the 2 disappeared, correct, thank you. Okay, so anyway, as you can see, this is, if you plug in x of 1, right? Y of 5.2, so does this make sense? Okay, very similarly, let's go to the second part over here. Okay, second part is 2. Okay, this is the second part. Okay, a of, so x of I is 2, right? Y of I 6.7. Okay, and multiplied by xi further. So in the first case, it was multiplied by 1. In the second case, this would be multiplied by 2. Anyway, you go through each data point, and then you add up all the a values, a coefficients, b coefficients. So this is what happens to the first equation. Very similarly, the second equation, if you recall, was partial e over partial b. It was 2, same thing, except over here it was 1, equal to 0, right? Okay, so for all the 4 points, you put in all the 4 equations, you add all the coefficients, you'll come up with this number, okay? Anyway, then you basically can put it in matrix form, as we discussed on the board. So if I go to the next slide. Okay, right? Then AB becomes this, A becomes 1.95, D becomes 3.51. So now we can plot y equal to 1.995x plus 3.1, okay? And if you plot it, this is what the red line will show up. These are the 4 data points. As you can see, through simply setting up a cost function, computing the partial derivatives, we are able to figure out the exact model that fits the data, that minimizes the error, right? Very quickly. Okay, let me show you a quick Python code, and I'll put it on the website. So nothing special about the Python code, but at least if you guys can start to play with it. Anyway, so this is the same 4-point data that I showed you. Okay, the same 2 equations, right? In using Python's matplot library, we can do a line plot as an example. So anyway, it does the plot, so if I run it,